Good morning, everyone. My name is Edgar Chavez, and I've been working with my mentor, Professor Hongsheng He, and PhD candidate Fu Zhongyang on developing a method for touch detection on any surface to be able to ease the collaboration between humans and robots working together to achieve a common goal. So a quick overview of what will be presented in this presentation is some background information, an overview of the entire augmented Omni surface and its methods, and lastly, the evaluation over the performance. So a conventional industrial robot are used to working on their own static environments, but as industrial robots advance, more human-robot collaboration is expected, since human-robot collaboration has indicated to make the manufacturing process more efficient and less costly and quicker. So being able to interact with robots by touch is much more natural for humans since touch is unambiguous, comfortable to use for long periods of time, and touch is something we're already familiar with. So take, for example, our phones, which work almost exclusively by touch. But we do run into two problems that prevent this type of collaboration for touch. First is being able to determine touch, and second is being able to recreate our surface as a 3D model. So take, for example, our phone again. The screen is a touch-sensitive containing a capacitive layer like many other touchscreen devices. But since we want to determine touch on any type of surface, that method becomes less convenient and more costly to implement. So determining touch on surfaces has been explored through several different methods, such as the items listed above, or a combination of the above items. But due to the development of commercial RGBD cameras, the prospect of turning ordinary surfaces into interactive surfaces is increasing. There are also several different methods for creating 3D models, one of which is using professional software such as CAD, CATIA, or Autodesk. But being able to use this type of software requires training, which will cost time and money. 3D scanners also work great, but they are expensive and have limited use for ordinary users. 2D cameras require the images to be high in quality, so for those reasons is why we choose to use the Intel RealSense depth camera to recreate our surface into a 3D model. Now the Intel RealSense camera is able to record the pixel information which contains the color and depth information to be able to recreate this model. Now here is an overview of the entire augmented Omni surface. In this phase, we are focused on the immersive touching aspect, but for future work we will want to add speech to further ease the collaboration between humans and robots. On the following diagram, we have an overview of how we can detect the hand and fingertip as well as create a model of our surface. For recognizing the hand, we use a VGGG, which is a visual geometric group structure, which detects our hand. And then we are able to use a deep learning model to be able to recognize the fingertips. Next, to be able to model our surface, we collect random points from the area around the hand, which contains all the necessary information to be able to create a 3D model of our surface. So we first start by creating an aligned image of both the color and the depth images. From our aligned image, we select random pixel coordinates from the area around our hand. And with the above pixel coordinates and depth information, we perform what's called the projection to transform these pixel coordinates into real-world coordinates. Now we can use these real-world coordinates to create a model of our surface. Here is a more in-depth model for our fingertip detection. You can see that we use VGGG for hand detection, as mentioned earlier, but we also have 3 other layers that output the information, that output the position of our fingertips in the input image. With that, we have all the information necessary to be able to determine if a fingertip is making contact with the surface or not. If we have a minimum distance d, which is less than or equal to the depth plus the average thickness of a human's finger, then the fingertip is touching the surface, else it is not. So we ran simulations on different types of surfaces, and for each surface we had 10,000 points simulated, including touching or not touching. So we computed the precision, the recall, and the F1 scores, and here you can see that the curved surface has the lowest result in all the categories. This is because we use the most extreme cases to test the performance of our model. In the following image, we can see that the augmented omnisurface method is being applied to different real-world scenarios. The last two images are grouped by a border, resulting in false detections, which is what we also consider to be our most extreme cases. This is because the reasoning behind this is that the working surface is too small, and the depth collection included more noise than desired points. So one solution for the working surface area being too small would be to decrease the area of points being collected and increase the number of points collected in that area. So to evaluate the acceptance of the augmented omnisurface method, we designed a questionnaire which we conducted on a convenient sample, consisting of 4 evaluation criteria. And as you can see, that criteria is correctness, ambiguity, effectiveness, and complexity. And from our results, we then calculated the analytical score out of 100% for each of the criterion. And from the graphs, we can see that the effectiveness scored the lowest out of all the criteria. So to conclude, we propose a method of touch detection for human-robot teaming using an RGBD camera to help ease the collaboration between humans and robots. And from our experiments and results and user acceptance questionnaire, they indicate that our proposed method is reliable. And that concludes the end of this presentation. Are there any questions? Yes, so from the other images, the entire surface covered our area, but for the 2 most extreme cases that we had, our targeted surface was that small cardboard box, and you can see the small cardboard box is taller than the desk that it was on, so there was more pixel points collected around the cardboard box than there were in our actual targeted surface area, which is why one of the solutions would be to make the area points being collected smaller, so it would focus more on our targeted surface. Yes, that is something that we discussed earlier on in the progress, but at this stage, we were more focused on being able to determine touch on our surface. As I mentioned earlier on, later we wanted to add other features.